that we were talking about last week and we started to discuss, actually it was about number systems. Because we are trying to some kind of formulate n-dimensional spaces, okay? And for that, we need to understand some kind of what is a point, what is a line, and this kind of things, which brought us down to the idea of what is a number. And we started from natural numbers. If you remember, we assigned the empty set to 0, or we have said that, okay, you can imagine a box such that it has nothing as the number 0. Then you can use this model of boxings in order to create 0, 1, 2, 3, and so on. Then we were also trying to look at some kind of equations. And we said that, okay, if there are no concept of negative numbers, for some of the equations we cannot find solutions. That is why we try to extend our number system from natural numbers into integers, right? But the thing was that, although we have some positive numbers and negative numbers, the whole integers, the issue was that, no, we cannot divide numbers, okay? And equations like ax plus b equal to 0 did not have a general solution all the time, okay? So that is why we extended the set of integers into their quotient field of rational numbers. And we try to understand what is happening over here. And as you may remember, we have talked that, okay, the field of rational numbers, which is a set equipped with two operations, an addition and multiplication. In this kind of a field, we can do addition, subtraction, multiplication, division, and this kind of things, okay? Was it enough for us? Unfortunately, no. Because we had some equations like x to the power of 2 minus 2 equal to 0, which we showed that have no solution over the field of rational numbers. So what happened is that when even we are trying to imagine that this set of, rational numbers, although even there are a lot of rational numbers between any rational number that you can pick, still there are a lot of gaps in between of these rational numbers. Those gaps were actually the things that were causing us not to have any solutions for equations like x to the power of 2 minus 2 equal to 0. Okay? What we need to do is that, okay, we need to extend again our number system. And the thing that we try to do is that some kind of trying to give meaning to these gaps and fills. And we did this by using Dedekind cuts, if you remember, okay? And we said that, okay, we have two sets. Take all of the rationals to the left of that as the lower part of our cut, and the rest to the right part, okay? And we called it cut if it had some special properties. And also we have discussed that if you create all of these cuts in rational numbers, put them all together in a box, then we have the set of real numbers. And we have also talked about this completeness axiom, that in the set of, or the field of real numbers, we have actually a complete field. Or this is an ordered field which has this property of having supremums for non-empty subsets which are bounded from the bottom. So what was happened is this, at the end, is a field. Let's review this first of all. What was the meaning of a field when we are saying we have a set and we have this multiplication and addition? It was meaning that we can do all of these operations, right? We have addition, we have the identity element for addition, we have additive inverse of all of the elements. This addition are associativity and they commute. This is structure, we called it the abelian group, if you remember. And we have checked that R and addition is actually an abelian group. Then we have also talked about the same structures about multiplication and R without 0. And we have also checked that this multiplication is associative and it commutes. We have an identity element for the multiplication, which is called this number 1. And for any non-zero element, we can find an inverse, right? Which means that we can add, we can divide, and we can do this kind of things, okay? Also, we have a relation that connects these two operations, multiplication and addition, which we call the distributivity law, if you remember. Besides being a field, which means that it is an algebraically structure. What other kind of structures can we talk about in the field of real numbers? One of them is that is a field which is ordered. And how can we define an ordered field? We need to have 4 properties, right? First of all, for all x, y, z in R, one and only one of the following holds. What is that? X is less than y, x is equal to y, or x is greater than y. This is called the trichotomy property. Trichotomy. What do we mean by this? Can you translate this into English? What do we mean by this? Any 3 real number that you can pick any 3 real numbers. I don't know, -5, square root of 2, whatever you like. Pick any 3 of them. This is just for 2. I will come to this z also, why I have to for all 3. Let me just, I can write it over there. Let's pick 2 real numbers, okay? What does this mean? It means that these 2 must be either equal to each other, or one of them is less than the other, or vice versa. Okay. Nothing can happen. We cannot say that, for instance, if you pick 2 numbers, they are going to be, for instance, less than each other and also equal to each other. This is not possible. Also, it is not possible that, for instance, x is less than y and y is less than x. Okay? Only one of these is going to be hold true. The second thing is that, now for all x, y, z in R, if x is less than y is less than z, then x is less than z. This is called transitivity. Transitivity. What do we mean by this? What is the meaning of this? Tamam, şuraya gel. For all x, y, z in R, if x is less than y is less than z, then x is less than z. Okay? How can we turn this into our understandable English? What does this mean? How do you interpret it? Can I learn your name, please? Elif, please go on.
If one number is lesser than the other number is lesser than the other,
Yes.
the first number is lesser than all of them.
Yes, exactly. What do this mean for us geometrically? Can this be some kind of interpreted as we can put all of them in a queue on a row? Yeah, we can guess it. Don't worry. Any set that has this kind of a relationship, a binary relationship of this, less than, it is going to be called an ordered set, okay? But for an ordered field, we need to have a relation, an ordered relation such that it is also behaving well with the operation of addition and multiplication of our field. Which means that we need to also have 2 if x is less than y, then x plus z is less than y plus z for all x, y. What does this mean? How can we interpret this? İsminizi öğrenebilir miyim? Yunus, buyur lütfen. Geçen haftadan hatırladım, pardon. Soracağım ama yine.
If we add the same thing in the both sides, this won't change.
Yes, of course. Which means that some kind of, if you add any number to both sides of an inequality, you are some kind of respecting that. Which means that we are some kind of shifting everything to right, and the inequalities is still remaining. Oh, not 2, this is 3, this is 4. If x is less than y, and we have a positive number, then x z is less than y z. What does this mean? What is the meaning of this? Please.
If you multiply numbers with something positive, then the relationship between them will change.
Yes, exactly. Which means that positive numbers, some kind of, are in good relationship with multiplication and order relations. Okay? If you have all of these 4 properties for a field, then we call it an ordered field. Okay? Now, when we are saying that the field of real numbers is ordered, what does it mean? It means that not only we can do multiplication, not only we can do addition, subtraction, and all of these algebraic things, but we can also compare real numbers to each other under these conditions. Okay? What else was the property of R? Which is ordered and is complete. What do we mean by complete field? It is actually the axiom of completeness. Completeness axiom. What was it? Do you remember? What was the completeness axiom that we have talked about? This was actually the axiom that showed us that when you're writing that decimal representation of real numbers, when we are saying, for instance, 1.4142 or whatsoever, and the infinity many times go on without any repeating and so on, this is actually the thing that tells us that this kind of things that you write, they are actually numbers. They are some meaningful mathematical objects. Okay? What was it? Would you like to remind us? You were saying?
Can I read?
Yes, of course.
Any non-empty and bounded subset of R has
Yes.
a unique least upper bound.
Yes, any non-empty bounded from above subset of R has a least upper bound. Or we call this supremum. We can also show that. If a set has a supremum, that supremum must be a unique number. So it is actually, if it exists, it is going to be a unique supremum. Okay? Let's look at some examples. We haven't yet talked about the geometric representation of real numbers, but assuming that you know this kind of things from high school, let's take this set, for instance. 0 and the square root of the interval. All of the numbers, all of the real numbers, which are greater than 0 and less than square root of 2. This is actually this set. Real numbers such that they are between 0 and square root of 2. Okay? Now, question. Does this set have any least upper bound? If we want to talk about supremum or least upper bounds, what should we look for? Completeness axiom, right? And in order to use this, we need to understand that if the set has some element inside of it, which is non-empty, now question, is the set a non-empty set? Can you please give me a member of that set? Square root of 2 is not there. We do not have equality. 1, for instance, yes, 1 is clearly inside of that set, right? So 1 is here. This is a non-empty set. Good. What about any upper bounds for this set? If this is going to be our set of real numbers, we are going to talk about it. If this is our set, okay, can you please give me any upper bound for it? And what was the definition of upper bound? It is a number such that all the members of this set are less than or equal to it. Which means that in this line, can you pick something that blocks this set from above on the right? Which means that everything remains on the left of that number that you pick. For instance, look at number 3 or look at number 4. Is number 4 around here or not? Is it blocking that set in such a way that everything is to the left of 4? This means that 4 is the upper bound for this set. And since we could find at least one upper bound, which means that this is actually a bounded set from above. Okay? Now question. What are other upper bounds of this set? 2 and 3, yes. Definitely they are upper bounds. What about all of the upper bounds? If you want to see what is all of the upper bounds of the set, where should we look at? To this place, right? So the set of upper bounds, is going to be which set? From the square root of 2 up until infinity, right? Good? Please.
Kökü dahil ettiniz ama orada dahillik var mı görmedim.
The square root of 2 is an upper bound for this set. Why? Because any element that you take from this set, it is less than or equal to the square root of 2. Is it or not? Look at the definition of the set. And the square root of 2 satisfies this equation, this definition, not equation, sorry. So what is happening? The square root of 2 is actually an upper bound for this set. Good? What else? Do we have any other upper bounds? We have listed all of them, right? No. The smallest of all of these upper bounds, what is that? The square root of 2, right? So, which means that supremum of this set is equal to square root of 2. Okay? Can you tell me about supremum of this set? Minus 1 and the square root of 2. Which is this set? This is going to be this minus 1 and the square root of 2. This is the set of all real numbers such that they are greater than or equal to x, less than or equal to the square root of 2. Is this a non-empty set? It is not, right? It is not an empty set. We have 0 here, 1 here, minus 1 here, square root of 2 here. We have many elements over there. Is the set bounded from above? Why not?
Because we have no exact value of
No, we are not asking about the exact value of the upper bound. I'm just asking this. Is there any number in this real line such that everything remains to the left of that number? For instance, if you take 3, can we say that any number here that you pick is less than or equal to 3?
Yes.
So, which means that this is a set bounded from above, right? What is the set of all upper bounds? If we collect all of the upper bounds of this set, what is that set going to be? It is going to be again this set, right? Square root of 2 up to plus infinity, right? Again, if you select the most least or the smallest one of all of those numbers, what is that going to be? What is the smallest element here in this set? And the set square root of 2. So which means that this is also square root. Okay? One other reminder, please.
In that case, is square root of 2
can be, what is the meaning of an upper bound? An element such that all of the members are less than or equal to that. Okay? Is anything from here less than or equal to square root of 2? Yes, so square root of 2 is an upper bound. So we can include it here.
I thought it was just.
No, not just the exact distribution. Okay, we also include equality as well. Good? So this is the whole case about these real numbers being a field, being an ordered field, and having this least upper bound property. Why we are very interested about this least upper bound property? It has many applications. We will see as we go on we will see a lot of things that we are going to depend on this, okay? But very important thing for us was that by having this least upper bound property, we could some kind of give meaning to decimal representations, or some kind of, we could say that, okay, irrational numbers actually exist. And all it is because of this least upper bound property. Okay? Is it clear, everything up to now? Good. Now, let's come back to this being ordered thing. If I have an ordered field, what type of different numbers do I have? Let's pick a number. Pick a real number, okay? Based on trichotomy, take x and another number 0. Based on trichotomy, what is going to happen to this number? It is either less than 0, it is either equal to 0, or it is greater than 0, right? Good? Let's define this function sign, which is from real numbers to real numbers, and define like this. If we have a positive number, sign of that number, we define it to be the number 1. For x equal to 0, the sign of x we define it as 0, and minus 1 when our x is negative. Okay? The meaning of a number is positive, a number is negative, is actually this. If its sign is 1, we call it positive. If its sign is minus 1, we call it a negative number. Okay? There was also another important function that you knew about it. Okay? We are going to talk about this, which gives us some kind of magnitudes of numbers, or absolute value. Do you remember that we showed absolute value? Let me come here. Absolute value of x, like what? First of all, this absolute value function is a function defined on R and gives us real numbers, right? PS of x, or absolute value of x, was defined as when we had a positive or 0, an x which is positive or 0. What was its absolute value? Which means that we are just trying to say what geometrically how can we give meaning to this absolute value function?
What's the distance?
Yes, it is some kind of distance from 0, right? We will talk about the idea of distance. What is the distance of a point from 0 when it is on the right hand side of this axis? The number itself, right? What about if it is on the left side of the 0? It is going to be minus 6, right? Good. Now, question for you to get some points as well. Can you draw the graph of this function and this function? Okay. Let's go on. still, yet given you the geometric representation of real numbers. But based on what you know from high school, we are going to draw two axes, the x-axis, y-axis, okay? When our x is positive, where I'm looking at, it is this part of our axis, right? What should it be? The value of my function. In all of these points, the value of my function is equal to 1, but not at 0, so some of you are drawing some arrows over here. Please don't do it. And also sometimes you're putting arrows down here and down here. Please also avoid that as well. Because as we are going to also discuss, and we have already discussed, the set of real numbers is an ordered set, right? So we have an order. Something is smaller than another. So they are coming after each other. With this, we are saying that which direction I have? Both directions? Which one of them is smaller than the other? Or this kind of things. So this is making some confusion. So please don't do this, don't do this. And also don't put any arrowheads over here. Okay? Good? At the point x equal to 0, what is the value of my function? 0. What about on the negative numbers? It is going to be -1. Right? Is it clear? What about the absolute value of x? Again, if you have this, what should we do? When x is greater than or equal to 0, we are drawing which function? Y equal to x, right? What was the graph of y equal to x? This is the graph of y equal to x, right?
Yes.
But I need to look at it in which place? When x's are greater than or equal to 0. So I don't look to the left-hand side of the x-axis, right? When our axis is negative, which means that when I'm looking at this part, what should I draw? Y equal to -x, right? What is the graph of y equal to -x? It is, yes, exactly, this kind of a line. But I'm just going to pick the negative side, so I'm not looking at this one. Okay? Fine? Good. What is the absolute value of -x and x? Can I say that this is true? Can I say that absolute value is always greater than or equal to 0? In which cases it is equal to 0? If x is 0. Is it possible that absolute value to be 0, but our x is not 0? Is it possible? Never. So, absolute value is equal to 0 if and only if x is equal to 0. Right?
Yes.
Good. What about this kind of a property? X, that's right. Doesn't matter. Can I say something like this? For two real numbers x and y.
Yes.
Why not? How can we argue about this kind of a thing? I mean that if you have two real numbers, if you add them to each other and look for their distance from the origin, it is this, right? It is going to be less than or equal to distance of x from origin plus distance of y from origin. Is this true or not?
True.
And if you have something to say, right? Please.
I think it's true because if both are positive or both are negative, then it's equal. And
Yes.
One of them is
Exactly. This is the way that we are going to argue about it. When x and y have the same sign, for instance, if they are positive, what is x plus y? Is it a positive number or a negative number? Y, by the way, how do you know that if we add two positive numbers, we can get a positive number? Recep, please.
Hocam eğer içerisi negatif olursa eksiyle çarpılıp dışarı çıkıldığı için pozitif olmak zorunda değil.
Dur, daha bir saniye. Şu soruyu soruyorum. İki pozitif sayıyı topladığımda niye pozitif sayı elde ederim? I'm asking this question. If I have two positive numbers and if I add them to each other, why do we get positive numbers? If x is positive, if y is positive, yx plus y is positive. We are not talking about this right now, okay? We have another question. If we have a positive number, x, I mean that if I have this x positive and if I have this y positive, okay, how can I say that their summation is also a positive number? Did we always believe at this, or can we really conclude this from some definitions or this kind of things? We had the definition of an ordered field, right? And if you remember, we had used to write that three properties. Go back to these properties and try to understand from which one of them we can really conclude this. This is coming from the definition of those things, right? I'm leaving this to you to check it out, because it's simple. If you go and just do that, you will see that. But it is not like that if you're adding two apples together, it is going to be like that. We have actually a grounded base for that. Why we are adding two positive numbers and the result is positive. It is coming from the relationship of this, the order relation and the addition. Okay? Good? Now, let's come back to what Elif is saying. If I have x a positive number and y a positive number, okay? I'm just going to argue one of these cases. The rest, again, you can also argue. If x is positive, what is this going to be equal to? Absolute value of x? X itself. If y is positive, what is absolute value of y itself? So this is going to be x plus y. What about x plus y? Is x plus y a positive number in this case? You have a positive number x, you have a positive number y. What about x plus y? It is positive. It is positive. So its absolute value is what? Positive. So this is also x plus y. We can argue exactly in the same manner that if two of them are negative, then this is also again equality. But in the case that one of them are positive, one of them are negative, then this is going to be strictly less than. Okay? Argue about this. Now, the thing that we are interested in the properties of this absolute value is that it is some kind of a idea of length to us, right? We are interpreting it as the distance from 0 up to some point, right? But I have this question to ask to you. What do we really mean by a distance? When we are talking about a distance, what is the meaning of distance? What is this distance? How can we define it? Lütfen. Dicle.
Length of point that has to do reference.
Okay.
Let's assume there's a reference and our point.
Okay.
The distance is the smallest length between them.
But how you are measuring that smallness, the smallest one? The thing is, if we're going to giving numbers, okay, assigning numbers to lengths and this kind of things, okay, instead of saying that distance of this point to this point is equal to this number, let's talk about the general properties of a distance, okay? If we have a metric or distance, what kind of behavior are we expecting it to have, okay? Can you please speak louder?
It should be starting from one point to go to another point.
What do you mean by starting from one point to another point going?
Find the distance we have to.
For example,
Yes.
it should be going from 1 to infinity
Yes.
or to 2.
For instance, if I want to calculate the distance of this with this one, right? What you're saying is that I need to start from one of them, go to other one. But can I also start from there and come here?
Yes.
So, what does this mean in general? Can we say that, for instance, we expect this distance metric or distance function to be some kind of symmetric? The distance of a point x to y is equal to the distance of point y to x, right?
It's like that.
Yes, some kind. That is why we are talking about absolute value function. Because we are going to use this in order to define this distance. But what other kind of properties does a distance have? Ali, please.
It must be linear. It must be linear.
It must be?
Linear.
What do you mean by linear?
Yeah.
Can we? If you always do this kind of a function which is linear, then what will happen if you are, for instance, trying to measure the distance of points that are not, linear, or they're not collinear or this kind of things? What will happen then? Let's take a non-empty set. Okay? A function from x times x, 3 numbers, is a metric or distance function on x if it has the following properties that we are going to discuss. First of all, what is the meaning of this x times x? Do you remember it? It was the Cartesian product of the set x with itself, right? For instance, if our set x is equal to 1, 2, 3, what is the Cartesian product of x times x? The Cartesian product of a set with itself or a set with another set is the set of all of these pairs, okay, x, y's, such that the first component is coming from the first component, second component is coming from the second component. Both of them are x here, okay? If our x is like this, so what should I write? I'm just going to write all of the pairs, okay, which contain these elements. What should I write, for instance?
1 and 1, 1 and 2,
Yes.
1 and 3,
1 and 3,
and 2 and 1,
2 and 1.
2 and 2, 2 and 3, and 3 and 1. Yes.
Good. How many elements do we have? 9 elements, right? Why we are taking these pairs into account in this definition? We are trying to define a distance on a space, right? I have this room. I want to calculate the distance of points here. But first of all, I need to have 2 different points, right? Or same points, who knows? But we need 2 points to measure the distance between these 2. That is why we are having this Cartesian product. Okay? Now, let me ask you this question. If I want to measure my distance from that column, okay? And if I measure it and come and say that it is -3 meters, do you really accept this? What kind of numbers? You are expecting it to be some positive number, right? So, first condition. For all x, y, z in x again, greater than or equal to 0. Okay? What about distance being 0? If the distance of 2 points are equal to 0, what can we say about them? They are the same points, right? What about the inverse of this? If we have 2 same points, what do we expect to have as a distance? But for instance, what is the distance of myself from myself? 0, right? So this distance, d of xy, is going to be equal to 0 if, and then we are writing 2f's. What does it mean? If and only if x is equal to y. Okay? What is the third thing that you're expecting from a distance, from a metric? We have talked about it, right? If I'm going to calculate the distance of myself from you, that distance is going to be, or must be at least, be equal to distance of you from me. Okay? So it's going to be symmetric, exactly. d of xy is going to be d of yx, which means that distance of x from y is equal to distance of y from x. Okay? The first one, which is called triangular inequality, is something like this. d of xy is going to be less than equal to d of xc plus d of zy. What does this mean? How can you interpret this triangular inequality? Let me repeat it here. D of x, y, it doesn't matter. X, y is less than equal to d of xc plus d of zy. What does this mean? Yes, exactly. Can you please also let us know your name? Elif. Good. What is Elif saying is that this says that when we are trying to measure the distance, always the shortest path is this measuring it directly, right? If I try to go to some other point and then measure it to there, then I'm always going to have bigger and bigger distances. By the way, why this is called triangle inequality? From Euclidean geometry, from maybe middle school, do you remember the conditions that if you have three numbers, when they can form a triangle? For instance, if I give you two numbers, 2, 3, and 11, can you draw a triangle such that has sides equal to 2, 3, and 11? The sum of lengths of two other sides must be always greater than equal to the third one, right? If this is not happening, it is not going to be a triangle. What is happening, what this imposes on our space is that actually if you have 3 points, x, y, or z, or whatsoever, you can form a triangle between them. And if you want to look at this distance, this is smaller than this one plus this one. If you look at this one, then this distance is going to be less than this one plus this one. If you look at this distance, this is going to be smaller than this one plus this one. Okay? That is the condition from Euclidean geometry that helps us to shape or form triangles. Hence it is called a triangle inequality. Now, question. R was a field. R was an ordered field. R was a complete ordered field. Is R a metric space? What do I mean by this? I mean that on the set of real numbers, can we define a function such that we can measure distance between any 2 points that we can take? If you want to say yes, we need to define some function like this that has these properties, okay? On the set of real numbers. So we need to define a function d from r times r into r itself with the following properties. Do you have any candidates considering this absolute value function? If I want to some kind of define the distance between the point x and y, okay? How can I define this? With this absolute value function that we have seen. What do you define it? You were saying it a little bit earlier. Absolute value of something. Please go on.
Is it the absolute value of 1 point minus the absolute value of the second?
I don't know, but we need to write it and check it down. For instance, this is a candidate. Do you have other candidates?
Teacher, not like this.
You mean this?
Value of
Okay, this is our first candidate. What is our second candidate? Absolute value of x minus absolute value of y. You say like this? Okay, good. What any other offers? Do you have any other offers? If we want to measure the distance between two real numbers, how should we do it? Can we, for instance, write, I don't know, x to the power of 2 minus y to the power of 2 is absolute? can also do that, right? It is going to be something like that. But let's check it out. First of all, let's go with this one. Is this a metric or not? What does it mean? It means that if it is going to be a metric, it must satisfy all of these properties, right? For any real number x and y that we can take, is it always true that the value of this expression is positive? You're saying no, right? But you need to give me a counterexample. You need to give me x and y as values such that if I plug it here, I say that, oh, okay, it is not going to be working. What are those numbers? Can you provide those numbers to me? Elif, please go on. I will come to you, don't worry.
If you say that x is 5 and y is 2, then, sorry, the other way around. If you say that x is a smaller number than y.
Okay, give me that number. What is 2 and 5? Okay. Based on this definition, d of xy equal to absolute value of x minus absolute value of y. What is the value of this? Then absolute value of 2 minus absolute value of 5, right? What is this equal to? 2 minus 5, which is equal to? Minus 3. Question, does this contradict with this or not? No. It contradicts with this. We need to have a measure, a distance, such that it is going to be a positive. Always it must be a positive number. Yes, we have calculated the distance between number 2 and number 5, and that distance is minus 3. Is this something acceptable for us? No, because we said that we should have positive numbers, right? You have something to add, please.
What if we put a rule that the biggest number should be here and the smallest one should be there?
Then we are going to have problem with the symmetric property. Then it's not going to be a symmetric metric. If you are going with this order. So this is not working. Please go on.
Maybe we can add another absolute value at the outside of the second one.
Yes, we can add also. As an exercise, check that also. But let me come back to this one. Okay? Let's first go with this, at this C1 metric, then we can talk about the examples of things that are not metric as well. So let's go with this. Is this always positive or not? It is always positive, right? Absolute value of anything is positive. So the first one is checked. When this is equal to 0, if this distance, if d of xy is equal to 0, what can I say here? If and only if, by definition, x minus y is equal to 0. What does this mean? If absolute value of something is equal to 0, what is that thing?
0.
That thing is 0, which means that x minus y is equal to 0, which is, if and only if, x is equal to y. So, am I true? This means that the distance of any point with itself is equal to 0, and any two points that have distance equal to 0, they are the same points. Good. 2 is also checked. What about 3? Is this symmetric or not? How can we check it? We need to use just the definitions, right? Let me come right here. What is d of xy by definition? Absolute value of x minus y, right? This is our left-hand side. On the right-hand side, what do I have? I have d of yx, right? Based on what we have defined, what is d of yx?
Minus y plus x.
Is it this or not? What is happening here is this. You need to look at it as just symbols here. Take the first symbol, put it here. Take the second symbol, put it here. Okay? If I have here this first symbol, then take it, put it here, then put it here. Good? This means that if I want these two to be equal, d of xy equal to d of yx, I need to have this equal to this one, right? Some kind of, I'm looking also at the end. I'm looking at the goal, okay? Now that I know this, can I write this equal to y minus x? Because if I write it as y minus x, then this is going to be d of yx, and I will prove that this metric is a symmetric one. Okay? Why that is true?
Because like absolute real value, it will be positive in this term. Like
This is actually true because of this. If you have x minus y, then we can take the factor out of this minus, which is going to be now y minus x. Is it true? And we know that absolute value of two number is multiplication of two number, or the product of two number is the product of their absolute value. So this is going to be absolute value of minus 1 multiplied by absolute value of y minus x. What is absolute value of minus 1? 1. Which when multiplied by this is y minus x. Okay? That is why it is true. Good? Now, the tree is also checked. What about triangle inequality? Can we say x minus z is less than equal to x minus y plus y minus z? How can you show that? What kind of an expression did we have before about absolute value less than equal to absolute value of something plus absolute value of something? That a plus b something. Can you please go back and review that? We said that absolute value of a plus b is less than equal to absolute value of a plus absolute value of b, right? So in mathematics, what we are trying to do is always this. Try to make problem into a simpler problem that we know how to solve it. Okay? We are always trying to make simpler and simpler and simpler cases. We know this, we have talked about this, but we still don't know about this. How can we turn this into this? Which means that also vice versa. How can I use this one in order to from this to get this one? Because you know, why I'm going to use this one and not other inequality or equality or whatsoever? Because you know, their structure is looking like same, right? What are the similarities that you notice? What do you see? What has happened here? In place of a, what we have written? X minus y. In place of b, y minus c, right? What is a plus b then? If we take a here, equal to x minus y. And if we take b here, equal to y minus z. What is a plus b then? So is it equal to this one or not? Equal to, let me write it like this, x plus. Are we done then? So we have a metric now. Now that we have a metric, what does this mean? It means that on the set of real numbers, we can also measure the distance of each one of these points. Now, the important thing here is that having a metric structure on the set of real numbers, we can do the following thing. Okay. When we were talking about the set of rational numbers, okay, we did know that they are ordered, they form a chain, but we also noticed that they have some holes inside of them, right? We were trying to some kind of complete these holes, okay, in order to have a solid line. This is our imagination from the real lines, right? But why this is true? I'm trying to say this. From geometry, we know what is a line. Okay? Let's take this line, call it x prime x. Okay? This is a geometric line. What does it constitute of? We have points on it, right? And this line, as our imagination and as our Euclidean geometry tells us that, You have no holes on the line, and you have a lot of points which are ordered. Okay? Now, question. How this is related to the real numbers? Because, you know, even before in the class, when we were trying to draw the real axis, we were drawing a solid line, right? Why it is true that the set of real numbers can be imagined as a line, as a solid line? I'm just going to take your idea, and this is what is going to happen, right? You're saying something is to the left, something is to the right, right? You're actually some kind of ordering the points. This is exactly what we are trying to do. First of all, I need to have a point 0, right? I need to have a reference point. Let's take our reference point O, okay? I'm taking a point and calling it O, okay? Now, define the relation being to the left of. Here I'm trying to some kind of trust your intuition. What do I mean by being to the left of? Define the relation being to the left of among points of the line. If I take point X here, for instance, I have used X here, let's use the point P. Is this point to the right of the origin O or to the left of it? To the right of it, right? So you naturally know what is to the right, what is to the left, okay? Is this order following this trichotomy or not? Which means that if I take a point P, is it either to the left of origin, is it the origin itself, or is it to the right of the origin or not? If I take a point, can it be both to the right of origin and to the left of origin? Can it be origin itself and on the right of origin?
Yes.
How can it be? How can it be?
If it's the same point, no.
No. Take a point, one point, take a point, this point maybe, this point maybe, this point maybe. Whatever you point, take it and have it, fix it. And keep your eye on it. Can it be both on the left-hand side of origin and on the right-hand side of origin? Can it be origin and right-hand side of the origin? No. So trichotomy holds. Now, if we say that the point P is to the left of point P prime. Let me show it like this. P is to the left of P prime. And if we can say that P double prime is to the right of P prime, or P prime is to the left of P double prime, can we say now that P is to the left of P double prime? So we have also transitivity. So we can actually be able to order the points of the line. Okay? Now, this is something ordered. It does not have any holes in it. It is something complete. Okay? The only thing that remains is that how can I, for each point that I'm taking from here on the line, assign a unique real number? Because if I can uniquely assign a real number to each point of this line, then I'm going to say that, okay, those set of real numbers that we have created a box full of all of these cuts and so on and so on, it is actually imaginable like a straight line without any holes and so on and so on. Is it okay? Now, let me ask you this question. If I pick a point here, for instance, P, what kind of a unique real number I can assign to this number P? If you were going to say that I'm going to assign this real number to this point P, what is the most natural selection that comes to your mind? If I this point I assign 0, for this point assign 0, for this point assign 0, okay? Because this is an arbitrary point, right? Then I'm assigning the number 0 for all of the points. So it is not putting it in one-to-one correspondence with real numbers. So it is not a good choice.
So there is one.
What?
One.
What do you mean by that? Okay. This is an arbitrary point that I'm taking from the line. For any arbitrary point that you pick, we need to assign a number. If for that arbitrary point you assign the number 1, you are assigning the number 1 for all of the points on it. Okay? Assign different real numbers for these points. When we were talking about distance, what was your imagination? We need to assign different real numbers uniquely to each one of these points, right? First of all, for the origin, or this point O that you're selecting, is it okay to assign the number 0? Let's assign number 0. For other points, what kind of real numbers should we assign? For this number P, for instance, if I want to show this number, this point P, with a real number, what should be that real number? To this point, to this point, to this point, okay? Assign the lengths of OP here. Okay? If I give you this real number 2, for instance, let's say that this is our unit. Let's call it E. Okay? Let's assume that the length of OE is equal to 1, so we can actually measure what's happening. Now, if I give you the number 2, and I ask you to show me which point on the line is number 2, how you are going to show that number to me? As I have said, what we are going to do is this. We have assigned the number 2 to the point that has its distance from the origin, and since it is positive, to the right of the origin, in 2 units, right? So take this OE, go 2 times, so this is going to be number 2. If I give you this point, for instance, what is the number that you are going to assign to that point? This distance, right? What about this point? Yes, again this distance, but with minus, right? By doing this, we are putting, let me write it here. By doing, let me write here. Thank you for letting me know earlier. By doing so, as we discussed, we assign a real number to each point uniquely, and vice versa. This means that this straight line and real numbers are in one-to-one correspondence. And order is preserved. Good? This is why whenever we are trying to show the set of real numbers, we are having this solid line with the arrow. And why we are putting the arrow here? In order to say that the set of real numbers is an ordered set. And the order is what? Being to the left is meaning that go in this direction. Being to the right or come to the right means that go in this direction. Okay? So whenever you are putting arrows to both hand sides, you are making an unforgivable mistake. Don't do it, please. Good? Now, this is the structure of R. Now that we have come so far, let's talk about R2 as well. If I want to have a two-dimensional space and I want to geometrically represent that, how can we represent the two-dimensional space R to the power of 2? How should we draw that figure? What is your ideas? He's offering something like this. Something like this and something like this. What is this angle between these two? Are they perpendicular to each other or not? But question. Can I also represent R2 something like this? What is the why not? The thing is that if we are going to represent the set of R2, okay? There are two vectors that are generating this, right? We are going to maybe talk about this, or these are some topics from linear algebra, but anyhow, let's review it. Are these two vectors that are generating the subspaces, are these two linearly independent? Lütfen artık bana katılın. These are two linearly independent, which means that these actually generate the set of R2. Or, for any points that I have here, I can assign two numbers related to this and this, right? For instance, for this, I'm just going to do this and this, okay? And this way I'm going to find the coordinates of this one and that one, okay? This is also possible. This is also possible. But why do you always are using this? Why this one and why not that one? When we are using this, you know, strange thing is that normally students ask, where are we using this kind of things? You're all using your phones, right? You're all using your phones. And in order to put your fingers and to know what is happening, you need to have a coordinate system that your movement can be followed. So we are actually using this in the real life. Just touch your phone and you have used it in the real life. Okay? But what you're saying is a little bit different, because I can't understand you, to be honest. You're talking about equations, dimension reduction and this kind of things. Angle of what? Can we measure the angle between these two? Do we have any measure? How can we talk about the angle between these two? Okay? We still don't know about angles. We will talk about them. But you're some kind of right. We will come to that point. What is happening is like this. When we are taking a point from here, what was happening? We were assigning, or we were interested in what? The distance of this point to the origin, right? Now if we have a new axis, okay, which is going to be between anything here up to here, right? As long as they are not on top of each other, or they are linearly independent, we can take coordinate axis, right? But the thing is that now, if I take this point in the second dimension, let's say, okay? What is the length of this here? The length is this one, right? Let's call it L. But what is the distance of this point from this subspace? What is that distance? That distance is going to be this one, right? Look at this. Is this distance of any point on this y-axis, equal to its length, or are they different? Is this D and L equal to each other, or they are different? They are different, right? You have a triangle here, you know. Is it true that they are equal to it? Hypotenuse can be equal to one of the sides? Cannot be, right? L is greater than D. Are you sure about this? What I'm saying is this. When I'm just going to create a two-dimensional space, what was important for me, as in the one-dimensional case, it was that the distance from origin should be equal to the length of that piece of line, right? Now question, if I add another dimension, let's call it, and if I take any point from this, is its distance from this space, which is this D, is it equal to its length on this line or not? When we can make these two to be the same things, just pick this, rotate it, and when it is some kind of 90-degree. Then look at this point. What is the distance of this point from this subspace? I'm just going to define this kind of what is subspace or whatsoever, but anyhow, you have taken in your algebra. What is the distance from this point and this line? This length, right? So that is the whole point of it. That is why we are doing it like this. Now, another question. If you have another dimension coming here, if you want to have a three-dimensional space, how should we place it? Should it be something like this? Should it be something like this? Or should it be perpendicular exactly? If you're going to write a three-dimensional system, okay? Should this be perpendicular to each other or what?
I think it should be like starting from the same point.
Yes. And why we are doing it perpendicularly? So this is the third system, right? This is the z-axis, and we have this. So we are rotating it, and we have just this. But why we are putting it perpendicularly? Because again, the distance of any point on this axis from this space, from this plane, should be equal to its length. That is why. Good? What we are trying to do, we are also trying to explore a few properties of R. Then we are going to build on top of these things, okay? We have talked about the field of real numbers, that we can do this addition, subtraction, multiplication, division, and this kind of things. We can order them. We have this completeness axiom. It is a metric space. And also a few other properties that we need to check for. One of them is this Archimedean property of R, which says that if x and y are two real numbers with x being a positive number, then there is an n, a natural number, okay, such that nx is greater than y. What does this mean? Can you interpret this? When we are writing this kind of mathematical statements, we need to be able to some kind of interpret it in our simple, everyday language, right? How can we turn this into what we are trying to say? Can you some kind of geometrically, because we have also said that, okay, we know that, we have talked about this, that real line can be represented like this axis. In this axis, what is happening? If, for instance, this is our 0, okay, and for instance, if this is our y, okay, what does this mean? Yes, there is a natural number, there exists a natural number such that if you, what is the meaning of n times x? It means that you are just adding x n times to itself, right? Let's take, say, you know, x is a very small number, if you can imagine it, or any positive, as long as it's a positive number, it doesn't matter, it is small, big, or whatsoever. By the way, these terms, small, big, these are completely meaningless things. In mathematics, something is small, what does it mean? Okay? We need to be precise about this, but anyhow, intuitively, if you select a very small x, okay, a positive one, which means that there is a length here, right? The Archimedean property of R is saying that we can take this small unit and add it to itself enough times such that no matter what real number you select, we are going to pass it over. Okay? It means that if you put this 1 times, 2 times, 3 times, 4 times, 5 times, 6 times, 7 times, we passed it. Okay? What does this mean? No matter farther away you take a real number, and no matter how small but positive real number you take, you can always add the small amounts together until you come and pass this first real number that you have taken. Okay? This is the meaning of this. But what does it mean for us? First of all, what we have said before. If here our x, because x and y are two arbitrary real numbers that I can take, right? If x is going to be 1, let's take x equal to 1, and y any real number that you can want. Preferably maybe positive, because natural numbers are positive. Then what does it mean? It means that for any real number y that you take, there is a natural number such that n times 1, which is n greater than 1. What does this mean? Any real number that you take, we can always find a natural number bigger than that, right? What does this mean then? It is also meaning that the set of natural numbers is not bounded from above. We can always find bigger and bigger and bigger natural numbers. Good? But if we want to prove this, if we want to show that something is like this true, how can we do this? Any ideas? Let's. And our assumption is that we are the first people ever that are coming to see this kind of things. We are the first explorers of this kind of things. Okay? How can we prove this kind of things? What is your ideas? Do you have any ideas? Give me some wild guesses. This is just a claim. And we want to prove this claim. Why this claim is true? Because, I'm just making a claim, right? I'm saying that this is true. Why it is true? What we need to do in this case, I'm also trying to some kind of show you the proof methods. That's why we are in the beginning of this course, we are talking about all of these kind of things. There is something called reductio ad absurdum. It is a Latin phrase which means reduction or reducing to the absurd. Do you know what is an absurd thing? Something which is meaningless, something which is contradictory in itself, is called something absurd. Okay? Maybe you can ask ChatGPT to write you some absurd lines. If you can see some examples, it is going to be very fine. Mathematically, what is reductio ad absurdum? It is like this. When we are arguing about something, what we are going to do is this. We say that, let's assume that the claim that you are making is completely not true. Its negation is true. Let's say that we are a liar and this is not true. Are we going to arrive to some contradiction based on assuming this fact is not true or not? If we can come and reduce it to a contradiction, then we are saying that, okay, the claim that we made, it must be true. Because otherwise, we are just going to turn it into an absurd situation, right? This is the power of reductio ad absurdum. Okay? So what is happening is like this. Let's say the claim is not true. So what happens for all natural numbers and we have nx less than equal to y. The negation of this statement that there is a natural number such that nx is greater than y, negation of it is what? Any real number that you get, there is no natural number such that this holds. Or for any natural number that you take, the reverse of this is true. Okay? Is this clear? How can I use this? What I'm going to do is this. Open up a set and put all of these nx's such that n is a natural number inside of a set. Okay? Now, is this set an empty set or not? Or if you want to write the elements of the set, what are those? X, 2x, 3x, 4x, and the rest. Okay? Is it clear? Now, is this an empty set or not? It is a non-empty set, right? For instance, what are its elements? The positive x, 2 times x, 3 times x, and so on and so on and so on. Is this set bounded from above or not? Why not?
There is no limit, we don't know.
We haven't yet talked about the idea of limits, but look at this. What do we have here? What is our assumption? We said that no matter what natural number you take, this nx is going to be less than equal to y. which means that all of these elements are going to be less than equal to y, right? By our reductio ad absurdum, assuming this negation of this statement, which means that if this claim was not true, if this claim was not true, then this set was a subset of real numbers which is non-empty and which is bounded from above. For instance, y is an upper bound for this set. Now, question. If we have a non-empty set, which is a subset of real numbers and is bounded from above, what can we say about this set? Do you remember the least upper bound property? We have talked about it today, about supremum. We have a non-empty set such that it is bounded from above.
There is some number bigger than numbers in the set.
This set has a supremum, right? This set has a least upper bound prop. Okay? So from completeness axiom, this set S has a least upper bound. Okay? Let's call that least upper bound or supremum of this S the number alpha. So what is happening here is this. You see? We take this x, then we have this 2x, then we have this 3x, and so on and so on and so on, okay? And we're saying that all of these are going to be less than this number y. So this set is a non-empty subset of real numbers which is bounded above. So I can say that, for instance, it has an upper bound, the lowest upper bound. Let's call this alpha the supremum of this set. Okay? Now look at this. Can I take this x out of alpha and say that this is less than alpha itself or not? Our x was a positive number, right? So if from a number I subtract a negative number, can I say that this is this true or not? True. Is there anyone who is not convinced for this? Is this true, right? No. Can this be an upper bound? Can this be an upper bound for our set S? Which means that if we take this alpha and come a little bit to the left of it, which means that if we come here, okay, alpha minus x, can this alpha minus x be an upper bound for this set S? You're saying yes. You're making a claim. Can you prove your claim?
Because it's less than y. It's the first thing that is less than y, and we don't know alpha is. But we know alpha minus x.
Okay, but the problem is this. What was the alpha?
We don't know. Like,
We don't know, but it is a natural number. It is not a natural number. It is a real number. I don't know the exact thing, but I don't matter about it. I look for its properties, not about name or whatsoever. What is this? Alpha? It is the least upper bound of the set, right? Among all upper bounds, this one is the smallest one of them. So if I come a little bit to the left of it, then this is not the upper bound. Because the smallest of the upper bounds was this alpha, right? Now, if I come a little bit to the left of this alpha minus x, can I say that? Can I say that there is some element or some number from this set such that it sits in this between? So can I say that there is an mx or a multiple of x such that it lies between alpha minus x and alpha? Can I say this or not? How can we argue about it? Assume that it is not like that, then continue and so on and so on and so on. Can I say that there is a member of the set lying in between of these two?
We can.
We can. Why we can?
Because n goes to infinity and there's like infinite infinities between
Okay.
two numbers, and mine subtracting of x from the alpha, there's two different numbers, so
Okay.
there must be infinity between them.
Yes, but how do you know that this is not bigger enough such that it can really pass above it. We can really pass over it without getting on that area, right? But what I'm claiming is that no matter what, you're always going to step in this area in between. Being infinitely many of them over there, this does not give us that. What I'm going to claim is this. We have actually a natural number m such that it exists between these two. Because if no member of this set comes in between of these two, then alpha minus x is an upper bound of it, right? If after alpha minus x, there is no element of this subset, then all of these members are going to be less than alpha minus x, right? But alpha minus x is smaller than least upper bound of this set. How can this be? Since alpha was the smallest upper bound, this should not be true. Which means that since alpha minus x is not an upper bound for S, some member of S must be bigger than alpha minus x. Which means that we have a natural number m such that alpha minus x is less than or equal to mx, which is less than alpha or whatsoever. I don't need that part. But look at this. What I'm going to do is take this and take this x to the right hand side. Alpha is less than or equal to m plus 1 times x. Look at this. Is this a natural number or not? If m is a natural number, m plus 1 is also a natural number, right? And m plus 1 times x, is it a member of this set S or not? It is. What was alpha? An upper bound. We have found, since it was an upper bound, it means that all of the elements of this must have been smaller than or equal to this alpha, right? But what is happening? I can also, let me argue about this also, that this cannot be equality. Okay? We also can talk about this. So let me also clean this. Okay? So what happens now? I have a member of S, this set, such that it is greater than its upper bound. This is a contradiction with the definition of upper bound. Upper bound means that all of the other elements must be smaller than or equal to this. Okay, so this is a contradiction. This is something absurd. From where this absurd thing is coming? From the assumption that this is statement, that this claim was not true. Which means that now this claim is actually true. Okay? This is a very important property of real numbers. Okay? When we are talking about limits, we are going to use this property. So please keep this in mind, that there is this kind of property. Whenever we have a positive number, we can add it to itself so much that we can pass any real number that we desire. Good? What do I mean by this? You remember, we have just talked about the square root of 2, right? But what about the third root, fourth root, fifth root, sixth root, seventh root, and this kind of roots? Are you sure that this kind of numbers also exist in the set of real numbers or not? Again, we are going to use the completeness axiom, and as a hint, assume this set. If we graphically try to show this, this is actually we are selecting this set, right? What is the square root of the nth root of x to this set?
Upper bound.
An upper bound? Is it the smallest upper bound or some other upper bound? This is the smallest upper bound of this, right? So you need to show that this set has a supremum or least upper bound, and that least upper bound is actually the nth root of x. Okay? So for this you need to also use the axiom of completeness, right? First you need to show that this is a non-empty set. You need to also show that it is bounded from above. Then you need to use completeness axiom. Good? These are some starred exercises. Almost all of the things that we require from the set of real numbers that have, they're all satisfied. There's only one thing remaining, that we need to also make this clarification between decimal representation of numbers and the reals. Then we are completely done. I think that they are going to be much more confident working with the real numbers because we have explored all of their properties and this kind of things. Now, let's write something like this. 4, 1, 4, 2, and so on. Actually, it is 0 point, all of the decimal representation of the square root of 2. Okay? We know that this is actually a number and not some, picture. If we are writing 3 divided by 0, we have discussed over it, right? We can write 3 divided by 0. Okay? Let me write it again. Yeah? So you really can see that we can write it. But as a mathematical object, does it have any meaning or not? We have discussed it that no, this does not have any meaning for us. But when you're writing something like this, an infinite decimal expansion, okay? We were also going to ask ourselves, and we have asked and talked about this, that is it also some picture that we can write? Or is it something mathematically solid? Does it really, as a mathematical object, exist or not? We have talked about this and we said that yes, these are really existing. Okay? But we also know that in the geometric way that we represent real numbers, we can show it by this solid line. But if I want to show this number, how can I represent it? How can I find it? If let's say, for instance, this is our origin, 0, and I have 1 here, how can I find this number? How can I plot it? Where is the exact location of this number? What? We can. Why we can't? We can. And how we are doing it is like this. We are working in base 10, right? We are working with numbers between 0 up to 9, and we have in base 10. It means that chop this into 10 equal pieces. I hope I can do it. Did I do it right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, good. And you assume that they are equal lengths. Okay? Now, all of the numbers has this kind of a starting thing. All of the numbers that this kind of a starting things. All of the numbers that have this. Where, in which one of these pieces these kind of numbers live? I'm going to say that in this place, all numbers whose decimal representations in the first place has 0 live. In the second one, all of the numbers with 1, 2, up to 0.9, right? This is some kind of a addressing of the points, okay? We have an address book, and this is an address, okay? And if we follow this address, we are going to find this point on the line. How can we do it? This is this. In the first street, which block should I choose? 0, 1, 2, fourth one, right? This one here. Let's make a zoom out of it, okay? Again, I'm going to chop this into 10 pieces. 2, 3, 4, 5, 6, 7, 8, 9, I think, okay? What are the address of these homes? Yes, 0.40. What about these things? 41. What about this? 0.42. And the rest follows, right? So it is clear what's happening here. So if I want to follow and go to this address, which one of these should I select? I'd select this one, right? Good. Now again, take this, chop it into 10 pieces. Let's again make a zoom out of it. Okay. Whatsoever. Okay. Then what is this address? 0.410. What is this address?
412.
412. When you're saying this is address, this actually shows this number. Okay? 41, not 2. 0.411 is exactly this point. Okay, and so on and so on and so on. So if I want to go to this address, which one of these houses should I select?
414.
4. This is 2, 3, 4. Right? I select this one and you got the idea. Okay? But what is happening is that instead of chopping it into 10 pieces, can I chop into 3 pieces? Can I chop it into 2 pieces as well? Can I chop it into 16 pieces? What does this represent to us? Decimal representation of real numbers in different bases. In base 2, base 3, base 8, base 16, and this kind of things. Okay? For instance, look at this. If this is our, again, 0, 1, I can do what? Chop it into 2. What kind of numbers do live here? Numbers with 0.0, here 0.1. If you chop this into 2, which kind of numbers do live here? 0.00 rest. What about here? 0.01, 0.10, 0.11, and the rest. And so on and so on and so on and so on. Okay? So all of these decimal representations are actually some kind of addressing of the numbers on the real line. Okay? Is it clear? Good? Okay. With this, we have almost talked about anything that we are going to use about real numbers. We were trying to find solutions for algebraic equations, right? And we have talked about many, many different equations. We didn't find a solution for them. We said that, okay, there's no problem with this equation. I am just lacking a worldview. I need to open up my worldview. I need to make a bigger world in order to be able to find solutions. The set of real numbers helps us a lot. But when we have this kind of equations, do we have a solution for this kind of equation in the set of real numbers? Why? You are all making claims. Can you prove your claim? Why there is no solution for this equation in the set of real numbers? I'll come to you. She's saying that a negative number multiplied by a negative number is a positive number. Are you sure? Do you know this, or you just take this as a belief? Because someone has told you, yeah, a negative number multiplied by a negative number is going to be a positive number.
We learned like this.
But we are going to question this kind of things, right? We need to think about this. We are not going to take anything that is given to us. Maybe they have taught us wrong. We should just take the. Now, question for you. Again, as a start exercise and this kind. Why multiplication of 2 negative numbers is a positive number? If we want to show that multiplication of 2 negative numbers is a positive number, what should we do? We should look at our axioms, right? About the things that we talked about, the order of real numbers, that 4 things, and multiplication and addition and this kind of things. You need to use that properties in order to show that it is true that multiplication of 2 negative real numbers is a positive real number. Can you use them in order to show that? Okay, anyhow, so you know that since x to the power of 2 is a positive number, if you add 1 here, x to the power of 2 plus 1 is going to be bigger than 1, which is going to be bigger than 0, which never is going to be equal to 0. Which means that this equation does not have any roots in the set of real numbers. But, shall we now say that, okay, let's just get hopeless, again forget about finding roots and solutions and this kind of things? Or shall we just, again, extend our worldview? What we are going to do is really try to extend our worldview. But what was happening is that almost more than 200 years, people have thought about this kind of problem. How can we give meaning to this kind of things? We are also going to maybe talk about Cardano's formula, about finding the roots of a third degree polynomial equation. But in that expression, people have seen that, okay, there is something wrong here. There are some numbers which are negative and they're under this square. But if you take them as something that really exists and you work with them, they are actually taking you into the solution. So what was happening here is that, oh, it means that maybe we can give a good meaning and good definition to square root of negative numbers and this kind of things. But how can we do it? But the problem is that since taking the square root is actually the inverse operation of multiplication, we need to some kind of have a good way to define our multiplication. But before coming to that, the point is this. Since we have the set of real numbers, this one, filled with anything, filled with everything, right? And no empty places to fill more. If we want to have new numbers, where that new numbers should exist? It was the point that, okay, let's do this. Instead of looking at points, at numbers, as points of a line, let's take this plane, and for each point of the plane, which we show it by xy, okay, let's assume that this is a number. We can do it, right? We have took, for instance, empty set for the number 0. We have taken the integer 0 as all of these diagonal numbers and this kind of thing. So we can actually create different objects and behave them as numbers, right? Again, let's do the same thing. But this time, points on the plane, we are considering them as numbers, okay? So the set of complex numbers is actually this r times r, okay? If I have two complex numbers, which is like this, still I'm just going to use this notation. How can we define their addition? Because what was our things that we were trying to go after? Define an addition, define a multiplication, and try to see that this set with that addition is an abelian group, with the multiplication is an abelian group, and we have distributivity law. So we were trying to some kind of turn our structure into a field, right? How can we turn the plane into a field? This is why complex numbers are important and they're coming into the picture, okay? But let's go and talk to this. If we have these 2 points or these 2 numbers and we can behave them like vectors that you know. If we want to define an addition between them, how can we define this addition? This is equal to this, which is defined as, how can I define it? If I take 2 points in the plane and add them, I want it to be again a point in the plane, right? So it must have 2 components. What naturally comes to you? How can I just make another thing here and here? Yes, add them component-wise, right? So it is going to be x plus x prime, y plus y prime. Good? Geometrically, what is happening here? This is the vector addition that we have learned actually. What we are doing is that we are drawing these parallel things, and this point is going to correspond to the point z plus z prime. Why? Because the x coordinate of this point is the x of this plus the x of this. So it comes here. What about its height or y? Yes, the y of this one plus the y of that one that we put on top of it. So this is going to be like this. What kind of properties does we have? You need to show that this is actually associative. You can do this. Z plus z prime plus z double prime. This is going to be z plus z prime plus z double prime. You just need to write them. Take this as xy, x prime, y prime, x double prime, y double prime. And if you write this, you will see that since these are addition of real numbers, these are addition of real numbers, And since real numbers addition are associative, this is also going to be true. By the way, I need to ask you something. You see an addition here, right? And also an addition here, and here, and here. Are they all the same thing, or are they different things? What is this addition? This is an addition between complex numbers. Okay? This is the addition between complex numbers. Yet we are going to define how to do that. This is again addition between complex numbers. Complex numbers plus complex numbers. What about this one? X is a real number, right? What about x prime? It is also another real number. So this addition is the addition of real numbers. This is also the addition of real numbers. These are inherently different additions, but in mathematics, since we do not use a lot of notations, we are just using the same notation for different things which are very similar to each other. This is called abuse of notation. Okay? We need to be very aware of this kind of things, that when we are abusing our notations. Otherwise, everything is just going to get mixed and everything is going to be trouble. Okay? When we are talking about set of complex numbers C, this is going to be called the real axis. This is going to be called imaginary axis. Okay? We can call it again x and y, but they're the same thing. And for the whole plane, we call it Argon diagram. I think he was, I don't know, a geographer, mapper, and engineer. I really don't remember. But he was one of the people who came up with this idea of putting numbers outside of these reals. So putting numbers above and below and this kind of thing. That is why we are referring to this. When we are having this complex number like this, the first component is called the real part of our complex number. We show it with re of z, which is x. And imaginary part of our complex number is also called the second component, which is y. Okay? Do we have an identity for our addition? Is there any point in this plane or in the complex plane such that if you add it to any other complex number, the result is also going to be again the same complex number? What is the zero of our complex plane?
I will say that is the number could be 0.
But what is the zero? What is the zero? This complex zero, let's say.
Okay.
It must have two components, right?
Yes.
What is the first component and second component of it? Which means that this. If I take this complex number and add this zero to it, I must have this complex number itself, right? Based on this definition that we have here, what we are going to get? Kim oradan bir sıfır sıfır dedi? Hangisiniz? Is this true? If I add this 0, 0, 0 here, which is this point actually, is this going to behave as the identity of addition? If I add this point to any complex number, the result is going to be like this. Okay? Good. So we have an identity. What about additive inverse? Additive inverse of any complex number. Which means that if I have this complex number xy, is there anything called minus z, okay? Such that if I add these together, I get into 0. Yes, exactly. Minus x and minus 1. So this is going to be as minus x minus y. Okay? If this is our point, z equal to xy. Okay? What is minus z in the graph? Yes, you need to reflect it with respect to the origin, right? So it is going to be this point. Minus is equal to minus x minus y. Okay? So we have also an additive inverse. What about commutativity? Can we change the order of addition of two complex numbers?
Yes, why not?
Can you prove this?
Like if you add, for example, 0 plus 1,
Let me give this as an exercise so we can also get some points. Take two numbers, complex numbers. Z is xy, z prime is x prime, y prime. Based on the definition that you see here, can you please show that z plus z prime is equal to z prime plus z? Okay, in order to show this, I'm just making it, right, as we have defined, right? So in order to show this, I need to show this. But what is the meaning of this? It means that component-wise, we are just going to add them. Component-wise, we add them. Why this is true? The complex number z, these two, are equal to each other if and only if their real part and imaginary part are equal to each other, right? If and only if x is equal to x prime, y equal to y prime. Which means that for two complex numbers to be the same, they must have the same components, right? Now look at this. Is this first component equal to this? Yes. Why? Because this is a real number, this is a real number, and this is the addition of real numbers. And we know that addition of real numbers is commutative, so we can change their places. So we can flip them. What about this one? Exactly the same argument. So we know that this is true. Since this is true, this is also true, this is also true. Which means that addition of complex numbers is a commutative thing. Which means that this C and addition is an abelian group. Fine? Now, let's try to some kind of define multiplication between complex numbers. Kapıyı açık bırakırsan çok seviniriz. Çok sıcak oldu burası. If I have this complex number, z times z prime. How can we define multiplication, which is a good multiplication, between complex numbers? Do you have any ideas? Make some guesses. Let's assume that we are the first people who are trying to build this kind of a system. What is your first thing that may come to your mind? How can I define this complex number multiplication? What should I write here? What should I write here? If my z and z prime are given by this.
Prime.
Fn, right? X prime, y prime. Okay. Is this really a good multiplication or not? Let me ask you this question. But by this being good, what I mean, it is like this. Is this the complex number 0 or not?
Yes.
What was the complex number 0? 0, 0, right? And for two complex numbers to be equal, they must have the same components, right? Is 2 equal to 0 and 0 equal to 0? So this is not 0. This is not 0. Okay? Let's, by this definition, take also this number. Is this also a non-zero complex number or not? This is also non-zero. By this multiplication, what is the result? 0, 0, right? You see what is happening? We are multiplying two non-zero numbers and we are getting a 0 result. This is not good for us because, for instance, whenever we are solving this kind of, equations, if this multiplied by this equal to 0, then we were going to say that, okay, either the first one is equal to 0 or the second one is equal to 0. And from there we were going to find the roots, right? But this is true only when something of these two, one of these two is going to be 0. If it is the case that our multiplication is defined in such a way that we multiply two non-zero numbers and get the 0, we can never conclude something like this. X minus 1 can be a non-zero thing, x plus 1 can be a non-zero thing, but their multiplication can be 0. So we cannot some kind of solve this kind of equations, okay? So this is not a good definition. What kind of other definitions can you define such that this set complex numbers, take this 0 out, okay? With that multiplication becomes a abelian group. I'm asking you this. How can we define multiplication between these two things, these two complex numbers, in such a way that it is really useful for us? Can you check what kind of problems do we have here? Because I need to also look for it, but as an exercise. Is the set of complex numbers except 0 with this multiplication defined, is it an abelian group or not? Check it, let me know about it. I'm not sure about it, I don't know. But this is also a good option. But historically what is happening is this. Let's assume you have this complex number z here, okay, xy. Look at this. Oh, how can I represent this x's and y's? If this is going to be our r, distance from the origin, okay, which we are always going to select the positive number, and let's assume that there is this angle of theta over there. How can I represent this point z using this r and theta? Look at this triangle. Look at this triangle. What is cosine of theta? This is x. This is y, right?
So x, y.
From here, can I say that x is equal to r cosine of theta? What about sine of theta? Y divided by r. And from here, what can I say about y? R sin theta. Okay? Good. Now with this, what is our z? Our z is r cosine of theta, r sine of theta. Which we can also say that r cos theta sin theta. Right? Is it clear what's happening? Now, let's take another point. Z prime equal to x prime y prime. Again, x prime is going to be maybe r prime theta prime, r prime, yeah, anyhow, okay? The thing is that the way we are trying to define multiplication of complex numbers is like that. First of all, take the theta of this complex number, which you call argument of this z. Take the theta of, or the angle of theta prime, the angle that it is making with the positive side of this x-axis. Sum them together. So this angle that's here, okay, this is going to be theta plus theta prime. Okay? And draw a ray. Okay? On this ray, we are going to take a length away from the origin, which is equal to length of this one multiplied by the length of this one. So maybe it is going to be here. And this length is going to be r prime. Okay? This way we are defining multiplication of complex numbers. Okay? What is happening is this. So it is some kind of rotating numbers. Rotating and scaling. How much we rotate as sum of their angles, and how much do we scale as the multiplication of their angles. Right? Some example. If we take this, okay, 1, 1, okay, and if we multiply this with itself, what is going to happen? First of all, what is this angle here? Pi divided by 4. What is this length? Square root of 2. Now, if I'm multiplying this with itself, first of all, what is my angle from the first number? Pi divided by 4. What is it from the second number? Again, pi divided by 4. If we sum them together, what is our angle?
90.
Pi divided by 2. So, it needs to be on this line, okay? But what is the length that it is going to be? What is the length of this? Is square root of 2, right? And multiplied by 2. So, a length of 2, it is going to be here. It is going to be 2, 0. Take a number here, take a number here. Let's call this x0. Let's call this x prime 0. Okay? If we multiply this together, what will happen? What is the theta of this? What is the angle that is making with the positive 0? What is theta of this? 0. What is the distance from origin of this?
2.
X. It is x.
Yeah,
Okay.
sorry.
What about this?
X prime.
X prime. Now, if we multiply these together, first of all, we need to know about the angle. What that angle is going to be?
0.
0. So the result is going to be living here. And what is the distance to the origin?
X prime.
X prime. So it is going to be something here. I think it's 0. Okay? Now, if for instance, we take 2 points from here and from here. Okay? What then will be? Let's take this again. x0, but this time x is negative. X prime 0, x prime is negative also. What is the theta of this one and r of this one?
0.
0? No, not 0.
I know.
Pi, right?
Pi is right.
What about the angle of this one?
Pi.
Pi.
Again pi. What about the distance from origin? X. What about distance from origin? X prime. Okay. If we multiply these two, what is the angle that they are going to make with the positive side of x-axis? 2 pi, which means that it will rotate, come here. So we are going to draw a ray here in this direction, okay? And we are going to select a distance which is equal to what? X prime. X was negative, x prime was negative. So x prime is a positive number. So it is really a positive number. And this is going to be here. So x prime 0. Look at this. If you want to multiply these two numbers, right? We need to know about their angle and their distance from the origin. The angle of this from positive side of the x-axis is what? Pi. What about this one? It is also pi, right? What are their distances? X and x prime, as we have defined, right? So when we are going to multiply these two, let me also write it here. Okay. Z prime, we defining it as r times r prime, their lengths, and also we are defining as cosine of theta plus theta prime, sine of theta plus theta prime. Okay? So we are summing their angles and we are multiplying their. This is pi, again pi. If you add 2 pi's, it's going to be 2 pi, so it is going to be, again come here, so it is going to be this direction. And what is the distance that we are going to take? The distance of this multiplied by this distance. So, is this looking like a negative number multiplied by negative number equal to positive number?
Yes.
Let's take a point here, let's take a point here. Okay? If we multiply this together, what's going to be happening? What is the theta of this one? 0. What is the r of it? X. What is theta prime of this? Pi. What is r prime of it?
X.
X prime. Okay? So if you want to multiply these two, what is going to be our angle? 0 plus pi, right?
Pi 2.
So what is this going to be? No.
Ah.
0 plus pi. So it is going to be what?
160.
Something like this, in this ray, right? What is going to be our distance? X times x prime. X is positive, X prime is negative real number, right? If we multiply them, is it going to be a positive real number? It's going to be negative, so it is really in the side. And what is that distance? It is going to be X, X prime, and 0. So look at this. It seems that this line is behaving like a set of real numbers. Also, what about their multiplication? If you're also multiplying these two things, when it is coming from this, you're just looking at the first component. Okay? Which means that we are some kind of putting real numbers inside of this whole plane as well. Okay? You will see about that when we are also going to talk about the algebraic representation of this multiplication. Is it fine? Now, let's look for another example. Let's look at this point. What is this point? 0 and 1. Okay? This is a very special point for us. We normally show it by I. Okay? What is the theta of I? Pi over 2. What is its R? Its distance from it? 1. Okay. Let's multiply I to itself. Can you please multiply I to itself? Yes, it is I. Algebraically, this is I to the power of 2. But what is the result? Which point it is here? Can you please show what? Minus 1 and 0, right? Why? Because when you're multiplying this I with itself, you're adding pi over 2 with pi over 2. So it's going to be like this. What is that distance going to be? This is going to be the point minus 1 and 0. Okay? No. We said that this axis is really behaving like the real numbers, right? So can I take this point? If I take this point as the real number minus 1, you are just going to show, I'm just going to show you that this is actually possible. I am able to make this kind of a representation. Just wait a few seconds. Then what is happening? You have I to the power of 2 equal to minus 1. What does this tell us? Yes, we have something. When it is squared, we have minus 1. Good. What does this mean? It means that it seems that I is some kind of square root of minus 1. So, notation. I'll just have it here. I squared, which is 0, 1 to the power of 2, is going to be minus 1. Okay? Please be careful that not to refer to I as square root of minus 1. Okay? Although it is behaving like square root of minus 1, but it is not square root of minus 1. Try to avoid this notation and always refer to it as this. I is a complex number whose, when multiplied to itself, the result is minus 1. Why I'm saying that please try to avoid using this? Because of this. Because if I multiply square root of minus 1 with the square root of minus 1, I can do this, right? I can say that, okay, this is the square root of minus 1 to the power of 2. And assume that they are behaving very well. All of the things, all of the algebraic operations that we know from the real numbers, they are true, let's say. Then what is this going to be? This is going to be minus 1, right? I can also say that, keep the square and multiply these two to each other. So what is this going to be? This is going to be square root of 1, which is, so we are going to go to this absurd situation of minus 1 equal to 1. Okay? Try to avoid using this notation. We are going to use it, but be very careful about it. Can you please also multiply this point to itself, which is 0 and minus 1, which is minus I. So it is actually becoming like this, and distance is equal to 1. Can you multiply this point to itself and see what is the result? we have 270 degrees. And if we multiply to it, we need to add 270 degrees with 270 degrees, right? And it's going to be make a whole tour and come here in this axis. What is going to be the distance? 1. So again we are at the point -1. Which means that I and minus I are some kind of square root of this number -1. Okay? So we have two distinct roots also. Then we were talking about real numbers, if you remember, and it was an exercise for you, that the second root of a real number is a unique number, right? If you have but here, second roots of any complex number, we are going to have two different square roots. For the third roots, we are going to have three different roots, and so on and so on and so on. We will come to that. But what I need to do is that I need to give you an algebraic definition for this multiplication, right? Because we are not going to do everything geometrically. How can we come to that? This is the first thing. The second thing that, look at this, please. If you have a point xy like this, let's take this point 1, 0 here. If you multiply any complex number with this 1, 0, what is it going to be?
Doesn't change.
1, this point multiplied by any complex number. What is the angle of this point? 0. What is the angle of this? Theta. Okay. If we add this, the angle is going to be what? Theta. So it is stay on this line. What is that distance going to be? Distance of this multiplied by distance of this, right? What is distance of this? 1 multiplied by distance of this. So it is the same thing, right? So this is actually behaving like a identity of multiplication, right? Let's show this with number 1, which is a complex number, okay? If we have this z, can you please introduce me another number which behaves like a multiplicative inverse of this number? Can you geometrically show me a number such that if I multiply these two, the result is going to be 1? What should we do for it? If the angle is theta, I need to look for something such that if I add that angle to this theta, that angle must be 0, because we want to come to this point 1, right? So it must be minus theta. Okay? Let me also clean here a little bit. Is it clear what's happening? If I take any complex number here, okay? And if we multiply this with this z, where that complex number is going to be? If distance of this is equal to r, and if I select a point here such that its distance is equal to 1 divided by r, okay? Then if we multiply these two together, what is r multiplied by 1 over 1? So this is going to be at this point, right? Which has this 1, 0, which is one of complex numbers, okay? So it seems that we can also find, of course, for any non-zero complex number, also what? An inverse. Is this something good? Yes, of course. Because now we can multiply them. We have an identity. We have an inverse. So we can do division of complex numbers. And so on, and so on, and so on. That is the whole point of it. One further thing. If this is our I, which is 0, 1, if this is our 1, which is 1, 0, and if I take any other complex number, can I represent this as x times 1, 0 plus y times 0, 1? From linear algebra. What did we say to this 1, 0? 1 of the complex numbers plus, for this point, what did we say? I. So this is going to be I times y. Which is going to be, if x is multiplied by 1 also, it is going to be, so let's take it as x plus I, y. Okay? So complex numbers can also be shown like this. We can also represent them like this. It is again the same thing. Instead of writing xy in this form, write it as x0 plus 0y. Can I do this? This is a complex number. But since the y of it, or the height of it, is equal to 0, this is like a real number, right? And the x-axis, this was behaving like the real numbers. So I can show this with this real number x. Plus, there is a trick here that I'm writing this complex number 0y with this y0 times 0, 1. Why this is true? Because I want to have this 0y. What I'm doing is that I need to have a real number and I need to rotate it 90 degrees, right? So I need to multiply this with I in order to come to this part, okay? So this is a real number, this is I. So this is going to be also written as x plus I times y. Okay? This is two explanations why any complex number can be written like this. Now, important question that remains is this. If we have this kind of a representation, which is called the standard or algebraic representation of complex numbers, and this is called the polar representation of complex numbers. From this multiplication, how can we write something which is given by x and y and this kind of things? Let me keep it here, but I will continue from here. You know how to open up this summation of cosine and sine, right? Can you please give me the formula? So it is going to be r prime. I'm also multiplying this number inside of this. What is cosine of theta plus theta prime? Can you please tell me the open up this. Söyleyin abi ya niye Yes. Cosine of theta cos theta prime plus or minus? Minus. Again I have r prime. So I'm also multiplying it here. r prime. What is this going to be? Yes. This is our first component. What about our second component? r prime. Yes. Sin theta cosine of theta prime plus r prime sin theta prime cosine of theta. Is it true?
Yes.
Now look at this. What did we say about z? We said that z was xy, which we represented as r cosine of theta, r sine of theta. Okay? And for z prime, it was x prime, y prime, which was equal to I prime cos theta prime, r prime sin theta prime. Now look at this. What is r cos theta? X. What is r prime cos theta prime? Y or y prime? I don't know. Which one of them? X prime. X prime. What about r sin theta? Y. What about r prime sin theta prime? Y prime. What about r sin theta? Y. What about r prime? X prime. R cos theta. X. R prime sin theta. Y prime. So this is actually becoming what? This is actually becoming x prime minus y prime, and you have what? X prime y minus plus x y prime. This is how we define multiplication of two complex numbers. Can you please multiply 1, 2 with 3, 1? Are you going to remember this multiplication? No. I also don't remember it. What is the secret to knowing it? It is like this. We have this z, which is xy, right? Which I can also show it as x plus iy. Z prime is also x prime plus I y prime, which also I can show it like this. I am going to let you to show that actually with this multiplication, C star, and this is abelian group. Okay? Which means that it is an associative multiplication. It has an identity. We have talked about it. What is identity of multiplication? Yeah, let's go and make some simplifications. You will see what's going to happen, okay? And show that this kind of, all of the algebraic things that we know about multiplication, addition, and this kind of things are true. Also, distributivity for complex numbers is also true. Which means that we can turn this C with addition and multiplication into a field. Now let's say that you have checked all of them, they are fine and so on. Let's behave them like complex numbers and multiply them to each other. What should we do? We should distribute like, now, x times x prime, x time, let me write I here, x y prime, plus this iy to this, which is going to be I, y, x prime, plus I to the power of 2, y, y prime. What is this I to the power of 2? Minus 1. So what is the real part of this complex number? This x is the real part of this complex number. The thing that is coming with this I is the imaginary part of it, right? So if this number is also a complex number, can you please write its real part and imaginary part? The real part is the part that has no I with it, which means that we are just going to write xx prime minus yy prime. And what is the part that is having plus I times, what do I have? xy prime plus y x prime. Is it the same thing or not?
Yes.
Okay, good. So never memorize this formula. Whenever you are given two complex numbers, just write them in this form, multiply it. Fine? Good? Okay. Now, look at this number. What did we call it? I, right? It was what? 0, 1. But this is 0 plus I times 1, right? Which is I. That is y the notation. What about this point? 1, 0. This is 1 plus 0 times I, right? Which is 1. That is why we call this the 1 of complex numbers and so on. Okay? Good? Now, or let me write this as x plus iy. If we have a complex number, and if we reflect it towards this axis, three numbers, okay? The thing that we are getting is called the conjugate of z, okay? Conjugate. If we want to show this z bar, how should we write it? It is x minus iy, right? Good? It is reflected like this. Now, what is conjugate of conjugate? The same thing, right? It comes back to z. If you reflect this and reflect this again, or x minus iy, x minus iy, x plus iy. Okay. What about conjugate of summation of two complex numbers? As an exercise, show that it is going to be behaving like this. Okay? One other thing is also that, can you guess about this? What about conjugate of multiplication? Koshta, what should I write here? What do you think it must be? Any guesses? Guess it. Hello. This is going to be behaving maybe, yes, and it is actually true. Check them that they're true. Use the definition. One other thing is that we have defined absolute value for real numbers. But what about complex numbers? What about absolute value or modulus of a complex number? How do we going to define it? It is going to be the distance from that point to the origin, right? If this is our point xy, what is that distance?
From 0 to
Yes. What is this distance? What is the absolute value of z?
x plus
Yes, square root of x to the power of 2 plus y to the power of 2. Good? One more thing. This is also important for us. If we multiply z with conjugate of it, what do we have? Can you geometrically see what is happening? If I have this, and if I have its conjugate, if I multiply this with z prime, z bar, what is going to be happening? Geometrically, how we can interpret it? Recep'e bir gidip geleyim mi?
Teacher, maybe square z. Square z.
Not the square root of z, but the square root of absolute value of z. Why? Because of this. This is theta, this is minus theta. What is their summation? 0. So it is going to be here. It is going to be a real number. It is going to be a real number. But what is this distance going to be?
1.
Distance of this multiplied by distance of this, right? What is this distance and this distance?
The absolute.
And they are both equal to the same thing. You can also show this that absolute value of z is equal to absolute value of. Can I write this? Can I write this in this form? I'm just taking it and bring it over here, right? So what is happening here? If I have z multiplied by some number which is going to be equal to 1, can I say that this is what? So, can I say that this, can I take this as multiplicative inverse of z?
Yes.
Good. We are also looking for if this is our x plus iy or xy, how can I write inverse of z? What is this? Conjugate of x. Conjugate of x is what? X minus iy divided by what? This to the power of 2 or this to the power of 2, which is going to be x to the power of 2 plus y to the power of 2. Which means that I can write this as plus I times minus y. So I have given you the field of complex numbers. I have defined addition, multiplication. I have given you the identity of addition, inverse of addition, identity of multiplication, and inverse of multiplication, right? So we are completely done with algebraic structure of complex numbers. Okay? Next week we are going to talk about that roots and this kind of things and the rest of the story. Thank you. Bless you all. See you.